Okay, this is going to be the recorded lesson for Chapter 4 for AP Statistics. This will be taught over multiple days in the class, but this video covers all of what we're covering in Chapter 4. So Chapter 4 has to do with, similar to what we did with Chapter 3, where we learned how we could display data if it was categorical in nature, except this time in Chapter 4 and also Chapter 5, we're going to be talking about numerical data instead. And there's some additional analyses we can do for numerical data. So we said back in the last chapter that there's two major categories of data here. Or one is called categorical and the other one is called numerical. And for categorical variables, we use things like bar graphs to display things, or we might display data in terms of a contingency table. And then we have to have different mechanisms to display things that are numerical. Okay, so we're going to talk about the numerical side of things now. Okay, well, when it comes to analyzing data for categorical, there's really only one thing we can do, which is figure out what percentage of the counts are in each category. So we end up having percentages when it comes to things like categorical data. We end up what percent is in a particular category or some category condition given a condition, right? Because we have numerical data now in Chapter 4 and Chapter 5 here, we have a lot more options for analyzing this data. We can start talking about things like mean and median and things like that. Okay, so we'll cover all that. First of all, graphing data. When we talked about frequency counts, when we had chapter 3 categorical data, we had something called a bar chart, right? And a bar chart consists of dividing the data into categories. So we have some sort of categorical variable like pet, let's say, where the values of the variable are different animals. And then we can show how the data is distributed across those categorical variables. So that's called a bar chart. If we have numerical data where we have something like, say, the run times for a race, then the values will be numerical, like say 23.5 minutes or 31.8 minutes or something like that. So there's a continuous infinite number of possible values that a particular piece of data in this data set could take, right? And a number represents that. And those numbers have a particular order too. Well, we can still kind of decide to have something like a bar chart. What we would do in that case is we would just divide this numerical range, which really has an infinite number of values, into subsections. We just basically take something that isn't categorical and force it to divide into categories. And these categories are called bins. Okay, so when we take a numerical variables axis like this and we divide it into equal size regions, those regions are called bins. And then we can count the number of pieces of data that are in each bin and form something that looks like a bar chart. But when we do that, it's now called a histogram. Okay, so a histogram is basically a bar chart except for numerical data where we've arbitrarily divided the numerical axis into categories. Okay, a couple things to note for bar charts, right? There are always gaps in between these, right? But for a histogram, these bars touch each other, and that's because they're covering all of the data. We might have gaps in the data, but the bins are right up next to each other, okay? And then for categorical data, the actual order does not matter, right? Because if we have pets, right, there's no particular ordering here, rabbit, dog, cat. It could easily have been cat, dog, rabbit. And that means that the shape that we see here is completely arbitrary. It just depends on the order, which doesn't matter. However, when we're talking about histograms, the order does matter. It's always increasing from left to right. So lower numbers over here and higher numbers over here. And that means that this shape has a meaning, right? If we see a lot of the data in the middle, it means the middle values numerically are where most of the data is, right? So the shape has a meaning for a histogram. All right, so here's some data. This happens to be the resting pulse rates of various women. And if we were to graph this using these methods, we could produce a histogram. We could divide the region, like say from the 50s up to over 100 here, into bins, and then count how many of each of these pieces of data are in each of those bins. And if we did that, we would get what's called a histogram, represented by bars of the same width, and then the heights represent the counts just like they would for a bar chart. If we decide to connect this with some sort of a smooth curve like this, where we kind of have a smooth curve that sort of replicates the shape of the tops of these bars, that's referred to as a density curve, right? So a density curve gives the rough shape of a histogram, okay? And we can use bars, and if we do that, that's called a histogram. If instead we want to represent each of the counts with a particular dot, then that is referred to as a dot plot. So a dot plot and a histogram basically are the same thing, except that we use the heights of dots stacked on each other. And we did that during the first day when we did that analysis on the hiring discrimination activity. We built dots out of how many of our fair lotteries contained a certain number of female pilots being selected, right? So histograms, dot plots, ways to picture the distribution of where the data is across the numerical values of a numerical variable. Okay. And both these, the histograms and dot plots, they automatically obey the area principle. And then there's another one called a stem and leaf diagram, or sometimes called a stem plot, which can also be used. So I'm going to take this data set and show how we can build what's called a stem and leaf diagram, or also sometimes just called a stem plot. Okay, so if we know that the highest value here is in the hundreds, and the lowest value here is in the 50s, we can just basically peel off the ones digit, like 100 or 105 just becomes 10 with a 5 for the ones place. You know, kind of separate the ones place from the tens. And if we do that, then each of these pieces of data we're going to write as a number. So this 56, I'm going to say, has 5 in the tens place with 6 in the ones place. So this is called the stem, which is the tens places, and this 6 is called a leaf, so I would write this as a 5 with a 6. So this is 56. The 5 is in the tens place and 6 in the ones. The 60 would be in the 60s column, so 60, 68, 68. So I just put the ones place here to indicate that there's another piece of data here that is in the 60s column. So this is 60, and this piece of data is 68. We have 72, 76, 80, 88, 64 would be here, 72, 76, another 80, so 80, a 68, a 72, an 84, a 72, and then 105 would be the stem 100 with 5 for the ones place. Okay, so what you can kind of see is, if you look at this, this is sort of like a histogram that's on its side, except that these are the low values down here and these are the high values. And by the way, you can make a stem plot either way, with the high values at the top or the low values, but they have to be in order, right? So if you kind of look at this, but if I sort of like made a density curve for this, it looks like this. It pretty much matches the density curve of the histogram of the data. It's just that here's where the low data is and here's where the high data is, going this way, right? And so the same thing, except going this way. So a stem and leaf diagram kind of gives a side view of the same thing as what a histogram would be. It's essentially like a dot plot, except that we have the actual ones place of the numbers here instead of dots, right? So one thing that's really kind of a bonus for a stem and leaf diagram that we don't see when we have a dot plot or a histogram is, when we have a dot plot or a histogram, then we don't get to actually recreate the data. Like if I look at this data, like I know that there's some data here between 60 and 65, let's say, but I really don't know if this dot is 61, 62, 63, 64, or 65, right? But if I have a particular number over here, like this 8, I know this 8 is specifically the data 88. So if from a stem and leaf plot, you can actually recreate the original data set if you need to. So there's an advantage to this. Okay, and then we have another version of this, which is called a split stem. So a split stem or stem plot, or stem and leaf diagram, stem plot, right, is going to look like this. Okay, and all that means is, instead of just having one row here for each of the decades, we split that into 2. So basically, like this 5 here is going to be 50, 51, 52, 53, 54, and then we'll switch to this version, this upper version, when we want to do 55, 56, 57, 58, or 59. So displaying that the same, I'll build one using the same thing here. 56 would appear in the upper half of the 50s. The 60 would be in the lower of that. 68 would be here. 72, 76, 80, 88, 64 would be in the lower half. Let's see, 68 is in the upper half. 72, 76, 80, 68, 7284, that's the lower half, 72, and 105. So if we go 0, 1, 2, 3, 4 in the lower half, the 5 has to appear in the upper half. Okay, so this would be the same data plotted with what's called a split stem plot, or a split stem and leaf diagram. And the reason we might want to do that is if we want more granularity, we want to be able to see more structure. Right? The right choice for which one to use kind of depends on the data. So you don't want things to be so compressed that you can't see a shape, but on the other hand, you don't want things to be so spread out that there's only like one piece of data in each column, and then you also can't see the shape. So there's sort of a sweet spot where you're kind of, you have enough granularity to see the shape, but not so much that you're compressing too much, right? And then we also need to always include a key. So a key would be something like this. If we want to say, okay, what does this 5, 6 represent? So we just include a key that says 5/6 equals the number 56, right? So always include a key when you make a stem plot. Okay. Next thing we want to talk about is whenever we're describing a distribution of data that's numerical, AP has kind of rules of thumb for what they always want to see in a paragraph that's describing any sort of numerical data, and we use an acronym to remember the things we need to include. The acronym is SOCS, SOCS, and they stand for these things: shape, outlier, center, and spread. So we'll dedicate at least one sentence in our paragraph when we're describing any distributions to describing the shape, a sentence for outliers, a sentence for spread, and a sentence for center. I usually put it shape first, then center, then spread, and I save outliers for the end. So what we're going to talk about here is in more detail what each of these things do, how we can get information to put in such a distribution, and then we would end up putting all of this stuff together in a single distribution. Okay, but you can remember this acronym SOCS for what we need to do, what we must include for full credit whenever we describe a distribution of numerical data. All right, so let's first talk about shape. So shape just is going to be a word that we use to describe the general appearance of the histogram. So if the appearance is roughly symmetrical, meaning that there's a bulge in the middle and then it falls off on the two sides, it doesn't have to be perfect, but if it's roughly kind of balanced like that, then we can call it symmetrical, okay? On the other hand, if there's more information kind of pulled out towards lower values like this, then that is called skewed left. There's a tail that's towards lower values. And on the other hand, if the data is kind of, tapering off, but there's a tail towards the higher values, that's called skewed right. The only other one that I probably should include in the notes is if you have data that looks like this, that's all basically the same, so it's flat, then instead we could call that symmetrical, that's true, but we might also use the term uniform, right? A uniform distribution is one where all of the data is just kind of evenly spread among all of the different values. Okay. So for the other things, center and median and outliers, we have to calculate what are called statistics. Okay, so the whole course is called statistics, but actually the word statistic has a specific meaning. A statistic is a single number that in some way represents the entire data set. That, by looking at this one number, we can glean some information about the totality of the data set. Okay, so the statistics that are available to us to describe the center of the data are mean, median, and mode. And mostly we use mean and median, okay? Mode, just to kind of get it out of the way, although we don't use it very frequently, is just the most occurring value, okay? So the most occurring value. And so the only way we really use it is if you have data that looks like this, like sort of a single hump, then we would call that unimodal data. In other words, there's a single most occurring value, so a single mode. If we have data that has kind of two distinct humps, then we would call that bimodal data because there's two modes to the data. And we won't encounter that very frequently in our class because most of the other statistics work best when we have unimodal data. But we can use this word if we see two distinct kind of humps there. Usually when that happens, that's a suggestion to us that this data set, we might want to split into two different data sets. Maybe there's one data set here and a separate data set here, and we should be analyzing those separately, right? But whenever, regardless of what the shape is, if we want to calculate these other things, the median and the mean, we always use the entire data set, even if there's multiple humps to it, okay? So the two main measures of center, which you can kind of think of as the most typical value, or most likely value, is the median and the mean. And the median is defined as the middle value. So if you lined up all the values from lowest to highest, it'll be the value that's right in the middle. And if we have an even number of values, then you take the average of the two middle values to get the median. And the median is often abbreviated MED. Okay, the mean, though, is what we call, in more specifically, the arithmetic mean, right? Which means we're going to add up all the values and then divide by the number of values. That's written by whatever letter we're using. We just put a horizontal bar across it. That's the symbol for the mean for the x's. And then this symbol here is just a symbol from Algebra 2 that says take the summation, sum up, or add all the things. So you just add all the data values and divide by the number of data values. So this is the average that we've been computing since, like middle school. Okay, so we have basically two choices if we want to address the center value when we describe shape, outlier, center, spread. When we get to the center one, right, we're either going to report that data values, that data set's median or its mean. Okay, all right. So let's compare those two. Let's look at a simple data set and compute the mean and the median of this data set. So let's say we had a small data set, 6, 7, 8, 9, 10. The way we would compute the median is it would be the middle value, which is this one right here, 8. And the way we would compute the mean is we would add those 5 numbers up and then divide by 5, which would give us also 8. So 8, the mean and the median in this case are exactly aligned, right? But what if we took this one data value and we just moved it further out, so it was at 20 instead of 10? What would happen to the mean and the median? Well, the median would be completely unaffected, right? Because the middle data value was unaffected by just taking a value at the extreme here and repositioning it, right? But the mean is affected because now we're adding up 5 numbers, one of which is larger, and still dividing by 5. And so the mean goes up to 10, right? So the mean is affected by the things on the ends. I'm just going to right now call the ends, right? The mean is really affected by that. Same thing if we moved the 6 down to 1 or something like that. But the median is pretty much resistant to effects, okay? In fact, if you wanted to kind of graph it with a typical sort of distribution, if you had a histogram that was symmetrical, the mean and the median would be approximately aligned here in the middle, right? But if you had skewed data and the data was skewed right, like we just showed there, where we had some data that was pulled off to the right, if there was data pulling this way, the median will tend to be unaffected by things like the tail of skew or by outliers out here, like points that are far away, but the mean will always be pulled in the direction of the tail or the direction of the outliers. So the mean, in our other case, the median stayed 8, but the mean was pulled up to 10. Right, when we moved a piece of data out here. So whenever you move data further away from the bulk, it pulls the mean with it in that direction, but the median stays mostly unaffected. And if the tail is in this direction, then the mean is being pulled downwards, so the mean would be lower than the median. Okay, so you should know this basic relationship of how the mean and median will be related. Okay, and because of that, there's some rules for what we want to use there. And we'll talk about those in a second. But before we get to that, let's talk about spread. So when we talk about spread or the variation, we want to talk about basically, now that I know the center, let me go back here for a second. Now that I know the center is roughly here, well, how wide is this center? In other words, is this data that's pretty wide like this? Or maybe we have data that's very narrow, but it's at the same center. So it's not sufficient to just give the measure of the center. You also have to say something about how widely dispersed the data is around that typical value, okay? And so that's referred to using words like dispersion or spread or distribution, amount, things like that. And the specific values that we can use are the range, the interquartile range, the variance, or the standard deviation. By far, the most commonly used one is the standard deviation. So we're going to talk about that one in more detail, but let me define all of these terms, okay? So the range is just literally the very maximum value minus the very minimum value. We don't use this frequently. And the reason for that is because it's too dependent upon just these two values, right? You could have like a data set like this, let's say like this, where in general it's really tightly grouped, but have this one value out here. And then that means the range would be this big. And that value is not very representative of the entire data set because it's so dependent upon this one value. So we tend not to use the range very much in AP statistics, but you need to know what it is in case you're asked a question about it. Instead, another way we can divide the data is if you were to line it up in values from low to high. So this is the minimum, and this is the maximum, and the median is the middle value or the average of the two values, okay? Then what you can sort of think of it as the median, right? The median is dividing the data into two equal halves, right? Well, if you then divided each half in half, so you divided the left half into two halves and the right half into two halves, and used the same rules as median. So you took the point that was the middle point of this data set, or if you had an even number, you could take the average of the two middle values. Then this point right here that divides the lower half in half is called the first quartile. And this value that divides the upper half into halves again is called the third quartile. And you could almost consider the median to be a second quartile, because what the quartiles are doing is dividing all the data into quarters, into 1/4. So 25% of the data is between the minimum and the first quartile. 25% of the data is between the first and the second quartile, which is also called the median. 25% of the data is between the second quartile and third quartile, and 25% of the data is between the third quartile and the fourth quartile. Okay, so then if we want a measure of spread, what we can do is we can say, all right, now that I've got these quartiles defined, let me kind of back those off again so we have a little bit cleaner picture. Then what you can do is say, let's just look at the first quartile and the third quartile. And if I take the distance between those two, then that is called the interquartile range, which is abbreviated IQR. So you take whatever value Q3 is and you subtract Q1. And what it means is, where is the middle 50% of the data? This is the middle 50%. So the IQR gives us a width of where the middle half of the data is. Okay? All right, so that's called IQR, and we sometimes use that as a measure of spread. Okay? Now, another measure of spread is called the standard deviation, which is based on the variance. So I'm going to show you formulas for it here, and then we're going to go into more detail about what this is. The variance is you take everything from the mean. Now, the mean might be very different. Okay, so let me actually erase this, and I'll show you what I mean. Wherever the mean is, maybe it's here. Let's say the mean is here. So this is the mean x bar. Every one of these data points is a certain distance away from that mean. Okay, it's a certain distance away from that mean. And so if I just take a data value minus the mean, that's giving me the distance that data point is from the mean. How far away is it? And since they could be positive or they could be negative, we square it to force all of them to be positive. And then we add them all up, and then we take the average by dividing by the number of elements. And we'll explain later why that's n minus 1. So this variance really represents the average distance squared that data is from the mean. Data is from the mean. Okay? And then the standard deviation turns out to be just the square root of that. I'm going to go into more detail about that in just a second. In fact, let's take a specific example here. So in this data set, if you were to compute the mean actually turns out to be 74.1. Okay? What I'd like to have is some number that is going to get larger if the data is spread out around that, and smaller if the data is close to that. All right, so let's take one specific value here, 68. Okay, and I know that the actual mean here is 74.1. Okay, by adding up all these numbers and dividing by the number of numbers. Okay, so if I just took 68 minus 74.1, I would get negative 6.1. Right, and right now this is about the beats per minute of heart rates that women had in this data set, right? Okay, now what I don't want to have happen is all these negative numbers, when I add them up with all these positive numbers, cancel each other out, because then we'll just get 0 all the time, right? So to avoid that canceling out, what we do is we just square that distance away, right? So if we square that distance away, it forces that to be a positive value. And so we have a bunch of positive distances squared, whatever these distances are, right? These were positive distances. These were negative distances. We square everything to make them all positive. We add them up and we divide by a number that represents the total to get the average distance squared. Okay, the problem is because we square the distances, that means that this would be in the units beats per minute squared, which is not the reading of the data set. So what we really want is something that has the same units. So we end up just taking the square root of that whole thing to get it back into the units beats per minute. And that thing right there is called the standard deviation. Okay, so the standard deviation is really the square root of the variance. And that's the reason why the variance is given the symbol S for standard deviation squared. Our symbol for standard deviation right now is going to be S for standard deviation. And so here's a formula for computing it. We will typically not do this by hand, though. So I'm going to show you in a second how to do this in a calculator. Okay, but I just want you to know conceptually what it is. Very frequently we ask questions about what conceptually something is. All right, so we have, let's go back here. We've got these things that we're using to describe a distribution. We have shape, right? And the shape, we have choices of things like symmetrical. We could use skewed left or skewed right. Right? And then we've talked about center. We have two choices for that. We could use median, or we can use the mean. And then we've got spread, and our main choices are standard deviation. I'll abbreviate it standard deviation like that. Or we might talk about the interquartile range. So we're building up all these things in our toolkit that we can use to describe a distribution. The last thing we need to talk about is how do you determine if a data point is far enough away from the rest of the data to be considered an outlier? All right, so an outlier, basically it just means something that's unusual, okay? But there's a very specific rule that we can use that is defined for an outlier, and that is more than just the fact that it seems to be separated by a gap here. You can calculate a distance away from this. So here's the idea. Let's say that we have the median of a data set, okay? So I have a median of a data set here. And then I know where Q1 is, and I know where Q3 is, because I could line up all the data and figure out where 25% of the data is, or split it in half, find the median, split the left half in half and find Q1, the right half in half and find that. And so this distance here would be the IQR, the interquartile range. Okay, and then what I'm going to do is I'm going to take Q3, and then I'm going to add to that 1.5 IQRs. So however wide this is, I'm going to go 1.5 times that out here. And I'm going to get to a location, a number, and that number is called the upper fence. And then the idea is anything that's outside that range is so far away from the bulk of the data that we would consider it an outlier. Okay, so the way you calculate what's called the upper fence is, the upper fence is this one down here. Upper fence is any data that's larger than Q3 plus 1.5 interquartile ranges. And there's also a lower fence. The lower fence is anything that's below the first quartile minus 1.5 IQRs. So if I go to the first quartile and I subtract off 1.5 IQRs, then I'm going to get to what's called the lower fence. And anything that's lower than that is considered an outlier. Okay, so there's these kind of strict rules for determining if something is an outlier, lower fence and upper fence. Okay, and we can calculate those things by hand. Now there's a second thing that we can use. If we tend to be, instead of using the median, because the IQR is kind of connected to the median and the quartiles, if instead we're dealing with a symmetrical set of data where we're using the mean and standard deviations, then another way we could determine that something is an outlier is just if it's more than 2 standard deviations above or below the mean. There's kind of 2 general criteria. We can use the median and use what are called the IQR rules. Sometimes these are referred to as the IQR rules for determining outliers. Find the upper and lower fence and determine if it's outside those fences. Or the other way is you can just figure out how big a standard deviation is and go plus or minus 2 standard deviations. If it's further than that from the mean, then it's considered unusual enough to call an outlier. All right. So if you're trying to summarize information, right, if we stick with kind of the median and the quartile approach, there's actually 5 numbers that are really important. The median, the max and the min, and then the first quartile and the third quartile. Those 5 numbers are referred to as the 5-number summary. And we can use those 5 numbers to create another plot for displaying data that's different than histograms and stem and leaf plots and stuff like that. And this one's called a box and whisker plot, or sometimes it's just referred to as a box plot. Okay, so a box and whisker plot basically graphically shows the values of the 5-number summary for numerical data. So you have some sort of a number line here with the possible values of the data that you're looking at, like race times or the heart rates of women or something like that. And then you draw a line here in the middle where the median is. You draw lines where Q1 and Q3 are, the first and third quartiles, and then you make a box out of that, okay? And then, typically we don't fill this in, but you draw what's called a whisker that goes from Q3 all the way out to the max, and from Q1 down to the min. And so that is referred to as a box and whisker plot. And in a box and whisker plot, the IQR, because it's the difference between Q1 and Q3, is the width of the box, okay? All right, so we can actually force our calculator to do this for us, and I'm going to show you how to do that in a second. Sometimes when you do a box plot or a box and whisker plot, if something is determined to be an outlier, like let's say that this max value of 105 is actually an outlier, then a lot of times we'll make the whisker stop at the last point that wasn't an outlier, and then we go ahead and just have a gap here and we put like an asterisk or a star for each data point that's an outlier. So that will sometimes be used to indicate that those particular points are far enough away to qualify as being outliers. So let's determine whether this is an outlier. The way we would do that is we would have to figure out what Q1 and Q3 are. And so let's say that I've gone through the process to figure that out. I've divided the data in half to find that the median is 72. And I've divided the lower half of the data in half and found that Q1 is 68. And I've divided the upper data in half and found that Q3 is 80. That means the interquartile range, or IQR, is Q3 minus Q1, which is 80 minus 68, which is 12. So the width of this box is 12. And then if I wanted to check where the upper fence was to see if this was far enough away, I would start at Q3, right? And then I would go 1.5 times this box out here. So there's one box, there's another half of a box. This is the distance 1.5 IQRs. 1.5 IQRs. So if I take 80 and I add 1.5 times 12, I get to 98. So 98 is where we call the upper fence. So anything above this line is considered an outlier. And so this point out here at 105 is definitely in the outlier region, right? And in fact, it's the only one because the next lowest point here is 88, and 88 is not on the other side of the upper fence. So this 105 is indeed an outlier, and we should identify it separately, separate from the rest of the data. Or we would say this data does have one high outlier, 105 is above the upper fence. All right, so let me go back here. When we're describing distributions and we write up a paragraph, it usually takes a while to describe a distribution because we have to mention SOCs, shape, outlier, center, and spread. For shape, we have to look at a histogram of it to see, is it symmetrical, is it skewed left, is it skewed right. For center, we have to calculate its median or its mean and report that. For spread, we have to calculate either its standard deviation or its IQR and report that. And for outliers, we're either going to check the upper and lower fences, or we're going to ask whether or not the value is greater than +2 standard deviations from the mean or less than 2 standard deviations below the mean, above or below the mean. Okay, and a lot of this will make more sense when we actually try this, right? I'm just kind of giving you an overview so that you know all of what we're doing is so we can eventually write a paragraph that describes a distribution. Okay, so the good news is that for the most part, we will not be doing these calculations by hand. We're going to use a calculator. So I want to show you various ways to calculate things with a calculator. Okay, let's use this data set, and I'm going to assume that you're using a TI-84 or a TI-83. If you have some other sort of calculator, then you'll have to read up on your own to see how it works. As long as it has statistical features, that's fine. But I'm going to switch this presentation to showing my whole screen so that you can see both the data and what I'm doing on the screen with the calculator. So let me switch that. And now I want to present my whole screen so we can see all of it, because I want to okay, so I want to, here's the slides, and then I also have this is an emulation program, which you can actually download. If you look online for Wabbit EMU, there's a program here that has a completely functional TI-84 in software that you can run. You can run them on Android phones. They don't have a version for iPhone, but they do for Android, and of course you can run them on laptops if for some reason you don't have a calculator. All right, so let's say we're going to work with this data set, which is the pulse rates of these women, and I want to get everything I need to describe this distribution. Okay, so the first thing we want to do is we want to enter this data into our calculator so that it can do all the number crunching for us. So if you see there's a button here called Stat, we're going to press that. Go ahead and press that. And then there is an editor here, right? It just says Edit. So if you hit Enter, then that's going to give you what looks like an Excel spreadsheet, essentially, right? Or like a Google Sheet spreadsheet. You can enter data in what are called lists. And by default, this says list 1, list 2, list 3. If it doesn't say that, you can go back to Stat and select Setup Editor, and that will reset your editor so that it's to default mode. Okay, so let's say we're going to use list 1 to contain this data. The way we enter it is we just simply press these numbers, like 56, and then hit Enter. And we'll just do that for each one. You can use a keyboard if you're using a computer as well, and hit the Enter key. So I'm going to do that, enter all of this data. And so see, it's just populating this list 1 with the data. And then I'm going to just use the up and out down arrow keys to make sure I've got all of it entered right. You can enter data in any order. It doesn't matter what order you enter the data in for single variable data. When we get to 2 variable data, we'll have to make sure that we'll use 2 lists, and we'll have to make sure that they match when we enter them across from each other. For this, we just have a single variable data. Okay, and then whenever you're in one of these kind of weird screens, to get back to the main mode, you're always going to push the second button and then the mode button, which is quit. That will quit back to the command line to start fresh again. Okay, so now that the data is in the list, if I want to make it display a histogram so that I can figure out its shape, we're going to go back into what we're going to do a special thing. We're going to use statistics plots. So you have to hit the well, let's do this first. Go to y equals as if you were graphing an equation, and make sure that there's nothing in there. If you have any equations in here, clear them all out. And then select the second button and then the y equals button. That will give you a list of statistics plots. And so we're going to go into statistics plot setup menu for statistics plot 1 by hitting Enter. And the first thing we're going to do is, with the cursor blinking on, we're going to hit Enter to turn that statistics plot on. Okay. Then we have to scroll down one and tell what type of statistics plot we have. Okay, we're going to use the third icon over, the one that looks kind of like a bar chart. That's the histogram one, and we click that, it will allow us to select the X list and the frequencies. So when we go down one, we're going to, for X list, this should say L1, which means list 1. If it doesn't, then we have to make it select that little colored L1 above the 1 key. And so what we have to do is, with the cursor on here, we select the second button and then the 1, and that will put L1 there. And then hit Enter to make that go in. And then that frequency should say 1. If for some reason it doesn't, hit 1 and then Enter. Or hit Delete to get what's out of there, and then hit 1 and then Enter. So once that's all done, we've got the statistics plot 1 configured to display a histogram of the data in list 1. So now we're going to quit back to the command line, second, and then mode. And then to display it, we're just going to go zoom. And then you can either scroll down here and select the option that says zoom stat, or you can just hit the number 9. Usually you just get in the habit of going zoom 9. And when we do that, this will now display a histogram of the data in the list that we selected when we set this up. Okay. To see what this is telling us, you can press the trace button. So select the trace button. And then what this is telling us is this bar of the histogram is going from 56 to 65.8, and it has a count of 3 in it. If I arrow over to the right, this one is from 65.8 to 75.6, and it has 7, and so on. You can keep doing that. Okay, now one thing I notice about this is that the calculator tries to pick a decent kind of bin width for this so that you get a decent picture, right? But a lot of times it doesn't give very nice like dividing lines. Like this goes from 56 to 65.8. Maybe I don't want that. Maybe I want this to go from 56 to, maybe I want this to be a width of, I don't know, 2. So if I want this to be a width of 2 instead of a width of whatever that is, actually that would be a little small. This, what is this now? 56, 65. 0.8 minus 56, so this is 9.8. So maybe I want to make this exactly 10. So I want maybe this to go from 55 to 65 exactly, and then this one from 65 to 75. So here's how you set that. You go to the window key, so you press window, and then you set the X min to where you want the first bar to start at. So I'm going to set that to 55, right? And then I'm going to set X max to just anything that's as far as I want to go. So this data goes up to 105. Let's set this to 110, right? But the most important thing is this X scale. See how that says it's 9.8? That will make each bin 9.8 wide. I want this to be 10 wide. So I'm going to set that to 10. And then leave all the Y things alone. And then now we want to display again, but we can't do zoom 9, because if we do zoom 9, it will recalculate these things for us. So instead, we have to select the graph button. So now when I select graph, you see what I've got is when I put the trace on here, this first one is now the counts in the bin width from 55 to 65. And this one is 65 to 75 and 75 to 85 and so on. Okay. Looks like I cut this off. So maybe I'd want to go and make this a little bigger. Maybe I make this 130 as the max and then hit that. Yeah. So I can see the whole thing, right? These are bins of 10 now, and we see all of the data. So one unfortunate thing about histograms is that their appearance very much depends upon how you set up the window. So you might have to play around with something for a while to get a picture. But based on that, if I'm going to make a distribution paragraph, and so let me do that. Let me jump up here, and we will slowly make a paragraph here for this on the next screen. In fact, let me just do that on another screen. I'm going to make a paragraph that describes this data, and I'll say the distribution of women's pulse rates is, and the first thing is I'm going to include something now that addresses the shape. So to me, this shape looks skewed right? There's a tail off to the right. So I'm going to say is skewed right. That'll be my sentence that covers the shape part of shape, outlier, center, spread. Okay, the next thing I'm going to talk about is the center, right? So for the center, I'm going to need to calculate either the mean or the median. Okay, now I should have talked about this at some point. Did I not do that? Yeah, okay. Let's go back and talk a little bit about this. How do you choose between the mean and the median for data set? Okay, I want to talk about this at this point. This is further in the notes. So statistics are considered resistant if they're not overly affected by skew or the presence of outliers. And remember we said that things like the median, that would be resistant to change. If I change a point out at the extremities, the middle of the data doesn't change, right? However, the mean gets pulled around by the tail of skew or the outliers that we have, right? And the same thing for spread. You can kind of think of, since median and IQR are kind of related because they're both related to the quartiles, if we're going to use median for the measure of center, we should use IQR for the measure of spread, the interquartile range, because Q1 and Q3 are also going to be less moved around by extremes at the outside edges, right? So we call the median and the interquartile range resistant statistics because they resist the effect of the tails of skew, and they also are not affected as much by outliers. So if you have skewed data, then you must use the median for the measure of center, and you must use the IQR for the measure of spread. Okay, now on the other hand, the mean and the variance and the standard deviation, those are not very resistant to skew. So the only time we should be using those is if we have symmetric data. You're still allowed to use the median or the IQR, but now it's okay to use the mean and standard deviation as the measure of center and the measure of spread, all right? And the reason why we might want to do that, as we're going to learn when we get to chapter 6, is there's more things we can do with mean and standard deviation that we can't do with the median and IQR. So if it's legal to use the mean and standard deviation because things are symmetrical, we really should use that. So you can kind of think of it this way. If you have symmetric data, use the mean and standard deviation. If you have skewed data, use the median and the IQR. So back to the program here, we're trying to figure out how to describe this distribution of women's pulse rates. This data is skewed, so I'm going to report the median of this data when I report the center of this distribution. But I have to get that somewhere. So how do I get that? All right, here's how we get it. The data is in there. Let's quit back to the command line, second mode, and the data is in list 1. So if you go back to the stat button, and you scroll over 1 to calculations, this first item, one variable statistics, will calculate all of the one variable statistics. So if I hit enter, you have to tell it what list to use, which would be list 1. So I would go second and then 1 if I needed to make that there. This frequency list, I'll talk about how to use that later, should be left blank. So if there's anything in there, hit delete to make it blank and then go down to calculate. By the way, if you have a TI-83, what will happen when you select one variable stats is it will just write the words one variable stats on the screen and then just wait for you to enter something. And so then you have to go ahead and manually know that you have to press second 1 to make L1 appear there. Right? And then you can just hit enter. For those of you that have a newer calculator like this, it'll give you a little entry screen that prompts you with stuff, and then you select calculate. All right, and then so it's reporting a whole bunch of things here. The first thing is the mean. So this is how we get the mean of the data. This S value right here is how we get the standard deviation of the data, standard deviation of the data X. And then there's 17 pieces of data in here that's usually labeled N, but that arrow means there's more. So if you scroll down, you get the 5-number summary. You get the minimum, which is 56. The first quartile, Q1, is 68. The median is 72. The third quartile is 80, and the max is 105. So this is how we can get the 5-number summary, and this is how we would get the median. And so in my distribution paragraph, I would add a second sentence, this time for the measure of the center. I would say, maybe I could just continue it. So this is the distribution of women's pulses is skewed right with a median of 72 beats per minute. Always use units if possible. Okay, so now we've addressed the shape as well as the center of this distribution in our description. Right, next we're going to have to talk about the measure of spread, right? So the two choices there are IQR or standard deviation. And remember we said that if we have skew, we should use IQR. So I'm going to have to calculate that from what the calculator gives me. So the IQR is the third quartile minus the first quartile. So for this data, the third quartile is 80 and the second quartile is 68, right? So I got those two numbers there, right? And if we compute that just with a quick calculation, that turns out to be 12. So we can continue our paragraph by saying with a median of 72 beats per minute and IQR, that's the standard abbreviation for interquartile range, of 12 beats per minute. And they have the same units as the data. Okay, the last thing we would have to do is address outliers. And on the previous screens, we already calculated that this 105 point is a high outlier. So we should add to our description a sentence that says there is one one high outlier of 105 beats per minute. So if we're asked to describe the resting pulse rates of these women, the distribution, we would write a paragraph like that. But behind the scenes, there's a lot of stuff going on to get the numerical evidence we need to have, okay? So we would have to run one variable stats in order to get the median and the quartile range to get IQR. And we would also have to set up a statistics plot to graph a histogram so we can see whether or not it's symmetrical, skewed left, or skewed right. All right. So that's how we use the calculator to do everything we need to try to describe distributions. So at this point in the class, what I'm asking people to do is to complete problems 1, 2, 3, and 4 on the Chapter 4 required practice packet. So go ahead and pause the video. Go ahead and look at those on Schoology, complete those, and then if you're watching this later, I'll have the solutions posted as well in the materials section. Okay, and then when you're done, unpause and we'll continue. Okay, so now that you've completed the Chapter 4 required practice packet, the rest of the notes here kind of give the step-by-step for how to get the histogram and the statistics for a TI-84. There's one other piece of data that we might want to look at and let the calculator do, and that is the box and whisker plot or box plot. So I want to show you how to do that as well. This is another way to check for outliers. So let's take a look at this. Let's go second mode to quit. We still have our data in list 1, or you can put that back in from earlier in the video. And if I go back to second y equals, and then I go back into statistics plot 1, this is currently set the way we had it before for doing a histogram of list 1. But if I wanted to scroll down one and then scroll down to one of these two icons here, these are both box and whisker diagrams. Let me show you the difference between the two. So the second one, the one that doesn't have the dots, if I select that, and then I quit out, and then I do zoom 9 to display whatever the statistics plot setup is, I get a box and whisker diagram for the data, right? And I can use trace to jump around between the 5-number summaries. The median's at 72, Q1 is at 68, Q3 is at 80, the max is 105, and the min is 56, okay? Now there was a second icon on there, so let me go back to second y equals into this menu. If instead of selecting the second box and whisker plot, we select the first one, which I'm always going to ask you to use, by default use the first one, then the calculator does an additional thing for us. When I do zoom 9, it does the same box and whisker plot, but it also calculates the upper and lower fences, whereas is Q3 plus 1.5 RQRs and Q1 minus 1.5 RQRs, and it automatically determines if any of the points are outliers. And if they are, it makes the whisker stop and it puts separate dots for that. So by using the first box and whisker plot, you can let the calculator quickly calculate and determine if they're outliers. So I can see that there's a 105 outlier using this method instead of manually calculating the upper fence. Okay, so also a very useful tactic in the calculator. So we're learning a lot of good things about the calculator. I would say AP Statistics uses the calculator by far more than any other math class. So if for some reason you don't have a calculator like a TI-83 or 84, 84 is the best if you can get that. Definitely try to obtain one because we're going to use it heavily throughout the whole year, and we're just scratching the surface here. There's probably 50 things in the calculator that we're going to know by the end of the year. Okay, one more thing I want to show you here, and that is if you have a box plot or a box and whisker diagram and you want to get a rough idea of the shape without any of the data at all. So the only thing I have about the data is this. I can still use something we call the aquarium technique to try to figure out about how much data is in each one. Because in these box and whisker plots, we know that there's 25% of the data between each of these lines, right? So what we do is imagine that you had an aquarium that had glass walls at the max and min, at the median, and at the quartile 1 and quartile 3. And imagine that you're pouring water in that represents the data. So you would take a pitcher of water and pour an equal amount of water in each of these parts of the aquarium, think of this as an aquarium, starting with the narrowest one. So if you poured the water, 1/4 of the data into this narrow one, this would fill up really high like that, okay? Right? But if you poured it into this region is about twice as wide as this region, so this region would only fill up half as far, right? This region over here is just a little bit wider than this, so it'll fill up almost as high as this. And this region over here, again, is just a little bit wider than this, so it'll fill up almost as much. And just with that, I can kind of use a density curve to get a rough idea of what the shape of this distribution is. It looks roughly like this. The data is roughly distributed like that. So that would be enough for me to say possibly bimodal, right? Or fairly symmetrical, slightly skewed left, even though I have no access to the data to type into. Let's take a look at the same procedure over here. So I'll start with the narrowest region. Imagine that fills up all the way. Okay, this region is more than twice as wide, a little bit more than twice as wide, so this will fill a little bit less than half as much. This region is wider still, so it'll fill up even less. And this region is a little wider than this, but not as much as that, so maybe somewhere in between. And that means there's going to be, this data has some sort of a really huge peak right here, and then kind of gradually tapers off. So this data is definitely skewed right, and has a very narrow standard deviation here, okay? All right, so that's just a method you can use to quickly get an idea of a shape of a distribution from its box plot. All right, we already talked about the idea of resistance statistics, and basically we're going to summarize it this way. Whenever you have symmetric data, I want you to use the mean for the measure of center and the standard deviation for the measure of spread. When you have skewed data, you have to use the median for the measure of center and the interquartile range for the measure of spread, okay? Let's see, couple things. If you want more data about exactly what's going on in this formula and why we're dividing by n-1, send me an email, and I've got a separate, more advanced discussion of that. I'm not going to do it here in the lesson, but I'll be happy to talk to people about that or ask about it in tutoring or something, and I'll tell you more detail about that. The other thing is, the textbook in this point, we don't do a lot of this in this chapter, but it does mention that you can sometimes transform data before you analyze it. And there's reasons for doing that when you have really unusual looking data. So we're not going to do a lot with this now, but by the time we get up to chapter 10, we're going to talk about more ways to do this. But I just want to get this idea in your brain. Okay, if you had data like this, let's say we had a histogram for numerical data, which was the income of individual people, and this is the counts of how many people have that, then, if you looked at that for a typical population, a whole lot of people would make less than $1 million. Right? But there's a very small number of people who have huge incomes, like 200 million, 100 million, 50 million, and so on, 2 to 3 million, 3 to 4 million, or something like that, right? So it's hard to get anything meaningful from this histogram, right? But if you were to take this data here, the income, and instead transform it by performing some sort of a mathematical operation on it. For example, take the log base 10 of the data. Okay, like take the log of the data using the log key. Then these big numbers transform into much smaller numbers because they're the exponents that produce 10 to that gives this value. And then if you plot the log of the income, logarithm of the income versus the counts, you get something that looks more nice, that has like a nice identifiable symmetrical mean and standard deviation and things like that. Okay, so sometimes we'll work with transform data, not so much now, but later in the course. But when you do that, you have to be careful if you have a histogram to label what you did. So this is not income any longer. This is the log base 10 of the income. All right, that's all I'm going to say about that at this point. Okay, this data is mostly about this whole chapter is mostly about single variable data, right? If we're looking at a histogram, the values of variables on the horizontal axis is the variable. So this is the variable here, right? Like test scores, let's say. Remember, even though this is numbers, this is not a second variable. This is not a second variable in a histogram. This shows how the data is distributed. What shape does it have in its distribution across the variables? But this is the only thing that's a variable, okay? Another thing that's mentioned in the book, so I'll mention it now, is that sometimes, for some reason, the book puts it in this chapter, you'll have something where you have data where the data is on this axis. So the variable is on this axis, and then this is over time. So if you're looking at the variable on this axis, but over time, this is referred to as a time plot, okay? And it's a good way to see how one variable is changing specifically over time. But this is a fundamentally different graph than all the other graphs we look at. And we typically will not talk about this more until Unit 2 when we are, because really this is two numerical variables, year and then a second variable like deaths per 1,000 people from cancers or something like that, okay? But if you encounter the value time plot, you can think of it as the one case in this chapter where the variable is in the y direction, and then we have the special x-axis of time, okay? Okay, just to point out again, so for chapter 3, we had categorical variables, right? And so we could have one variable where we have like a variable gender, and then we have the count of that variable. Or maybe we have like two variables, like gender, and then what's your favorite flavor of ice cream between chocolate, vanilla, or other, right? Or we could have, in chapter 4, we're talking about numerical data, right? Where we have a numerical variable age, and this just shows the counts, right? Or we'll talk about this starting in chapter 7. We're going to talk about what happens if you have two numerical variables like age versus income. We have to do something called a scatter plot. We haven't covered that yet. Talk about that in Unit 2. Okay, but I just want to remind us of what the variable is. The variable is gender here. There's two variables here, gender and favorite flavor. The variable here is age. This would be a special case that we haven't considered yet, so we won't talk about that. Okay. All right, and that's it for chapter 4. So there's a lot more going on in this chapter. Please diligently work the practice. We've covered the basics to get you started, but you're going to have to really check it, work the problems, ask questions, either in the Google Meets, or if you can't come to that for whatever reason, try to ask questions of me in tutoring, check answers in Schoology when they're posted, and that'll be it for this video.